Today is part 2 for the TruNest Advanced Digital Manufacturing webinar series. Today we're going to cover punching and router fabrication for some sheet metal applications. So today we'll take a look at optimizing our material usage as well as integration with MRP and ERP systems, bringing in CAD geometry and BOM information, bill of materials from Inventor seamlessly through our Vault integration with TruNest. And we're going to look at some cutting techniques for automatic tooling for punching and routing, some use of some special tools for punching, common line routing and punching, cutting, repositioning, skeleton cutting, and special types of tabs for both of these different processes. So I am Matt Thorn. I'm a senior manager at Magestic Technologies, in charge of product and customer success here. So I'll be taking you through this today. Before I do that, I wanted to kind of give you, again, some background if you weren't with us last time on what TruNest is at a high level. So really, TruNest covers industries and materials for transportation, aerospace, construction, and wind energy power generation. We've been around since 1991, really specializing in integration and automation of production in our customers' facilities. So just range of materials. We work with metals, woods, composites, leathers, plastics, really anything that's 2.5D materials, thick or thin, doesn't really matter. We can support all these different material types, as well as the different machines that utilize these materials. So today we're going over some of our CNC routers and punch presses, but we also cover laser machines, water jets, plasmas, oxy-fuel, and combination machines, so punch route, punch laser, things like that. And we do write all of our post processors for these machines as well. So just to give you an idea of kind of the workflow that we're going to go through today, TruNest can bring in geometry from native CAD data, generic CAD data like DXF, DWG, IGES step files, things like that, or even legacy NC data. So if you're using things like AutoCAD or Inventor, those are very well integrated within TruNest, but we can also bring in outside data too. If you were working with, say, SolidWorks or Pro-E or something like that, we can certainly support that kind of data as well. We can also wrap a PLM or PDM component around that. So in this case, we're going to be looking at Vault and how Vault stores things, and how we can kind of get things from Vault within TruNest without kind of having to search all over to find the files that we're interested in manufacturing. From there, we process all this information and we send it to the shop to be able to run different machine tools, whether it's lasers, punch, plasmas, water jets. And all the time we take this information from sales orders as well as material inventory. We generate reports from all the nesting and things like that from this process as well. And at a higher level, we start to integrate ERP and MRP to drive information from these sales orders, from inventory, track things throughout the shop, track remnants, track material usage, all these different things to give you, the user, information about your entire process. So I'm going to switch it over and jump into the software. So give me 1 second.
While you're doing that, Matt, just posted something for questions. If anybody has questions, please put them in the questions tab there on your in your session, and we'll try to answer it at the end of the webinar.
Perfect. So here I've got TruNest up. And the first thing that we see when we open TruNest is an authentication screen. The authentication screen is necessary for us to log in with the username and password. I'm going to log in as an admin here. And the reason why we do this is so that we can account for what users are doing within the software, whether it's bringing in geometry, creating nests, or managing inventory, materials, things like that. We know what each user is doing, so we can understand from a tracking basis what's going on in the system. As well, once I log in here as an admin, it's going to also log me into a particular workflow or set of tools that I'm able to use. So as an admin, I can log into any of these different groups, and this is going to set kind of my permissions or my workflow within the software itself. So I'll go ahead and log into that admin workflow. It's going to bring up the software. And up top, we have the ribbon, which has a tailored workflow for my administrative tasks, some of the more used options within the software. And then on the left side here, I have the tree, which is all the features and functions within TruNest as well. I can actually switch between groups. So if I wanted to see what the engineering by default has available to it, I can kind of switch that over. And now it's a more tailored workflow for just a default engineer within the software. So bringing in materials, managing material databases between design and manufacturing, managing part constraints, grain constraints, things like that. And downstream for the shop floor, their workflow is the rest of the process, which is creating orders for production, scheduling those orders, creating those nests, manipulating parameters on the nests, generating that NC code, and then eventually sending it down to the machine tool. So you can kind of customize these workflows and add workflows as you have different potential users and use cases in your own production scenario. So I'll switch back over to an admin. So the first thing that we need to do with TruNest is we need to bring in geometry. So on the left here in the tree, I have that first step here. That's my part import. So there's really three main steps in a basic workflow that I'm going to be taking you through today. That's bringing in geometry, creating our orders, and then creating our nests. So we'll start with this part import process. So there's a couple different ways, as you can see, to bring parts into the system. The first way is through parametric design. So by default, we have a couple different parametric shapes available within the software that we can access. So if I wanted to create some rectangles or circles or things like that on the fly, I can certainly do that with just some input parameters within TruNest. If most of my designs are already created or already drawn, I can bring them using some of the other options here. So the first option that I have here is translate. So translate allows me to select a list of files, and what it does is it is a one-to-one representation of the geometry file to a TruNest geometry file. So what we do is we interrogate the source data and we create our own internal geometry file that we store manufacturing information inside of that file. So we're looking for tooling information, things like that for the particular processes that are currently loaded into your environment. We sort of store them with the part file so that downstream we already know how to manufacture that part after it's nested. With an automatic process, we go after geometry as well as any metadata within that file. So this is what we're going to be using for Inventor native data because as we go after assemblies, we have access to information like the bill of materials, which has material quantities and some other properties about that particular assembly. And we can bring all that information at the same time and start to fill out some of the part requirements automatically before we get to the nesting process. And then the last one here that we're going to be using today is our Vault integration. So our Vault integration does the same as that automatic process that I mentioned before, but it goes one step further and it saves the time for the user to have to kind of go through their computer and find the files and assemblies that they need to bring into the system. What this does, I can give it a list of assemblies, and it'll actually go into Vault and essentially do a get command and bring those locally to my machine. TruNest will interrogate those files for what it needs to, and then it will remove those from that client computer, all while not changing any revisions or versions or anything from Vault. So the assembly that I'm interested in for this demo is called punch route. So I'll go ahead and use this option. It's going to ask me to log into my Vault. I'll go ahead and give it my credentials. And it's going through a search process. So it's looking for that assembly, and it's bringing any files that are associated with that assembly to my machine. It's going to give me a status. So if there was any problems that happened with that download, if certain parts were in a certain revision, or if they weren't released to manufacturing, things like that, it's going to show me here and show me that they're not available for me yet downstream. After that process, it's going to do this translation process that I talked about. It's going to go into that assembly and find all the relevant files that I'm looking for inside of that assembly and translate them into individual TruNest files. All the while, it's maintaining material information, bill of material information, part thickness while we do this process. Any issues with that process? Say in this case, I'm getting a warning saying that some of my shapes are actually too small for the tooling that I have associated to the machine. So it's giving me these design constraints at the time that I bring the geometry in, so that I can go and potentially fix these things upstream in the design rather than having errors as I go try to run that on my machine, or if I try to post that and I get some issues with the post-processor, things like that. So it's trying to give you these warnings up front so you can deal with them before you go and go all the way through the workflow. So I'll just say OK to those warnings. And you can see some of the parts that I bring in here. This is the assembly information. This is the part information, material, and thickness. So this is the metadata that I was talking about that we were interested in. So as I go through these files, you'll notice these parts are colorized based on the tooling that's being applied here. So in this case, we're bringing it in for a router, so we can actually investigate some of the information about the layers, color, and style. So these drill holes essentially are colorized to that specific drill in the tooling library. So we already know that information, that circle on that part, is a drill hole since it matched up to something in our library. We already know how to process that, and that manufacturing information is carried through downstream to nesting and to post-processing for the machine. So we can kind of look through and investigate some of these parts, make sure there's no open contours, things like that, things that will need to be fixed. And it seems to all look good. So I've translated in my assembly. If I wanted to, I can go into what's called the part assembly review and start to modify some things about that assembly. So if I go in, I can kind of filter and see all the metadata that was brought in from that assembly. So now I see a couple different things. There's a quantity of 5 of each of these 2 parts that was brought in, a quantity of 20 of this particular part that was brought in. The grain constraints were already applied to these parts as well. But as I look through some of these parts, some of these parts are really nice for the punching process, like this one. I'd rather punch this part than route it, since it's got a lot of different holes and I don't want to necessarily make all those drill cycles. So what I can actually do is I can flag TruNest and say, hey, I only want to process that on a particular machine. Similarly with this one. These internal shapes, I really don't have specific punch tools in order to punch those, so I'd rather route those and then drill out the holes there. So I can actually flag this for a specific machine group. And what that will do is when I schedule it, it will only be available for that particular machine. So we'll go ahead and flag that one. And I believe there's one more as well that I want to flag, this one as well. This one's not really optimal for punching since it is a large contour. I'd have to kind of nibble all that out, which would take a lot of time. So I'll go ahead and flag that for routing as well. So I can do these things in the part assembly. Most of the metadata is already assigned for me, but I can make these small tweaks as well if I need to. So the next step is our order entry step. And at this point, it's giving me a snapshot of all the parts that are in the system. I don't necessarily want to order everything that's in the system. I only want to order that particular assembly. So what I'll do is I'll just go ahead and filter this. So I can start typing my assembly name in. This will kind of help me autofill to the rest of the assembly name. And now I've got only a list of the parts that I want to use on this nest. I can give this order a particular quantity if I want 1 or 2, however many I want of this particular nest. I can give this a due date. So do I want it done by today, tomorrow, or next week? I can also give this a priority. So this will influence the position of this particular order or even a part. It'll influence the position of that part on the nest. So if I need to add something that I really need right away, I can give it a higher priority, and that will influence it to be to the front of the nest. I can also give this a job order, and this will help me kind of maintain some of that information for that order downstream as well. If I wanted to manually sync to ERP or something like that, I can give this a job order. TruNest can also kind of order per facility. So if I had multiple sites or something like that, I can maintain all the information within the same environment, within the same database that TruNest runs off of, and then just kind of tag that appropriately to which facility that I'm interested in, as well as giving this a comment. So I'll go ahead and add that order, and I'll put that information down below. And if I wanted to, I can add another assembly, whatever I wanted to, and just gather up this large queue of parts in order to make sure I drive efficiency on like materials throughout my process. I can also do this process automatically. So I can drive the same process from an ERP or an MRP system through direct database integration or through exports like export imports from CSVs or Excel files, things like that. So I'll come over to schedule orders, and we've got our 2 different machines here. We've got all of the single job that we ordered, the due dates, things like that, the amount of unique parts, the amount of total pieces for this particular order. And you'll notice that there's 12 unique parts for the punch and there's 14 unique parts for the router. So because I made that change back in our part assembly to flag those 2 individual parts to only be run on the router, they're not even an option for the punch machine. So it helps me downstream make sure that every time I order that particular part, I know it's only going to be run on a particular machine. Additionally, I have some other dates here for cut and filler. These help me maintain when I want this particular nest to be cut by, as well as what date that I want to continue to add filler parts to. So a filler part is something that you keep stock of and potentially produce a lot, to where if we add it into the nest to gain efficiency, it's not going to be a burden to keep some stock of those in your shop. So we can add those filler parts automatically to drive up efficiency of your plates, but it's not going to add any more plates than what your original order would have been anyway. So we do track everything by status. So notice the status is currently active, which means I need to schedule them in order to nest them. So down here, we have some different statuses, and I'll get into those into a second. And the last thing here that I want to touch on is the hours and the plates. We do give an estimation based on the machine properties, cut speed, rapid speed, things like that, for the amount of time that it's going to take to process these parts, as well as the amount of material that it's going to take to process these parts. So it gives you an estimation there, so it helps you better plan for your capacity within the shop. So down here is a snapshot of everything that's currently in the system. So we have a lot of different orders that are currently in the system for the punch and the router, with, again, all these different estimations on the hours and the amount of material that are currently being used for those nests. So this allows us to give kind of see a snapshot of how much time is currently queued up for a particular machine. Would it be better to run this on one machine versus another? We can kind of make those decisions before we schedule it to better improve our throughput. So go ahead and actually select both of these. So I want to run the same parts on both these machines and kind of see which results that I want to run downstream. So I'll go ahead and do that and go ahead and hit schedule. So I brought my geometry in, I've created my order, and now I'm going ahead and creating my nest. So I've got that group that I just scheduled here. It's also in my table down below in this scheduled status, waiting for me to be nested. So I'll go ahead into the create nest, and I'll run the go ahead and run the router first. So I'll run the router, and it'll go through, and what it's doing now when I click that button is it's going through and it's nesting these parts on the available plates that I have. So you can see the different inventory sizes come up here during nesting. And after the nesting is run, it's going to go ahead and create reports, as well as run these optimizers for the specific cutting process. So in this case, we're running our automatic tabbing and our sheet cut for the router, as well as the post processor. And what these are doing is it's automatically placing tabs onto the part so that these parts don't move or potentially cause issues on the nest. So go ahead and open that up. So all these little white dots that you see are the tabs on the part, and those are holding it to the sheet. The lines that you see in the background are actually the sheet cut optimizer, and what they do is it breaks up the sheet into smaller pieces to allow for easier removal of the skeleton after cutting is done. And what's special about the routing process, typically with routing machines, the material is held to the bed via some sort of vacuum process. And the more parts that I cut out of that material, the less vacuum that's going to be there, and parts could potentially move. So that's why we want to tab them to the skeleton in order to make sure that they're not flying around or potentially causing safety issues. But in this case, what we're doing for these tabs is a special process called a skin tab. So a skin tab is something that leaves like an onion skin thickness. So we process through most of the thickness of the material except for that minor onion skin in this case. And what that does is it never fully removes that particular tab from that part, and it maintains that vacuum pressure better for that particular sheet. So that's something that we do special for the routing process. So we can kind of look through our different nests. in the different parts here. And as well, if we have any material that's left over, what happens is we create a specific remnant code for that. And depending on your process, we can either save that remnant for you and put it back in the inventory, and we'll use that remnant the next time that we go through the nesting process on that particular material. So we'll go ahead and reuse your remnants. We'll automatically process that remnant for you with that sheet cutting optimizer. So you can kind of see that there. It's highlighting on the edge of that remnant. So you get a clean cut that you can store back and use later for other nests as well. So let's go and run the punch process now. So we're going to go through the same thing. It's going to go through, it's going to create a nest for those parts. But this time it's going to run some different optimizations for the cutting process that we have now. So in this, and for punching, we still run tabbing and sheet cut, because those are vital to the punching process as well. But you can see here it's running a nibbling process. So what this is doing is it's running an automatic tooling routine for both the internal and external contours on every part. And it's processing this based on the tool library that's currently set up in the system. So it's going to go through, it's going to punch out each part on that sheet based on your current set of tools. So whatever rounds, rectangles, squares, special tools that you have in the library, we'll try to optimally use those on the parts that we've currently nested. So this allows you to essentially not have to tool all these yourself. It'll go through and do the tooling process automatically for you. So it's just doing the last plate here. And it's running the post processor. We're getting some warnings about our turret setup. So we're managing both the turrets in each case for the router as well as the punch press, and making sure that we have the appropriate tooling available loaded in the machine to be able to process these nests. So if there's any station changes, things like that, that need to happen, the post will warn you and make sure that you are running with the appropriate turret settings for the nesting. So we can see here all the automatic tooling that's being done for these parts. We can kind of zoom in here. So we have all of our tabs again. We have some of the circles and rectangles. We have our trapezoid tools for our parting tool. For some of the tabbing, this leaves a thinner tab or a thicker tab on the part, so it has more sheet integrity as we're processing the sheet. You can see the sheet cut is being processed as well with that tool. So everything's been punched out. We can see some of the destruct cycles that are going on within a part internally. So if we can't hit out an internal part with one single hit, we'll go ahead and automatically destruct that. We can kind of see some of the different results here as well. For the different parts. So we've automatically tooled these 3 plates here as well. So once we're done processing the nests, we have a lot of information available to us about this particular nest. We have a HTML report that we can take a look at and view, and this will give us a snapshot of everything that happened on that nest, what our efficiencies are, what settings we used for our plates and materials, all those different things. So it'll go ahead and give you all your nesting parameters, what your kerf was set on the machine, what your cut speed and rapid speed settings were, what your separation of parts are, what your efficiency goals were for this particular machine, and material. You have all the different part previews and all the different grain constraints that were used, the different quantities that were used for these parts, the inventories that were tried. So you have all that information inside of the report. And then per plate, there's also a different report. And this gives you a list of all the different tools that were used to process the nest. So you can see the total hit count, the description, what stations they were, any different tooling changes that might need to happen are going to be flagged here. So you can see T01 was used a couple different times in this. So it's telling you that essentially you would need to either open up another station for that particular tool, or if there was no other open stations available, tool change would be required. You can also look at the NC code that was created. So here you can kind of comb through and search for whatever you want to do. If you're looking for a specific G or M code, you can look for those and kind of search those out, and it will go through and highlight all those for you. And we can do the same for the router nests as well. So again, the turret report will look a little bit different. We'll have different tools and different stations, but essentially the same information, size, offsets, things like that for the tools, as well as how many different contours that tool was used on. And again, NC code for that as well. It was all created from that create nest option. And then to round out our process, we go into manage nests. And here I have some more functionality to be able to push this to the next stage in the life cycle. So we can see here some of the status is now either staged or rejected based on my efficiency goal. So we can see the nesting efficiencies here for each plate. And based on those, I either get a staged or rejected status based on my efficiency goal for that material. If something like 26%, this was the plate with only a couple parts on it, which had the remnant. If I didn't want to create that remnant, I can do things like push this back to that scheduling process to wait for more parts of the same material and add those parts together to gain more efficiency downstream. If I wasn't in a rush for these parts or something like that, I can certainly do that. I can do things like repost if I needed to, if I made any particular changes or modified some position or something like that. I can repost to make sure my NC code is up to date. I can also do a backplot. So a backplot will show you a reinterpretation of the NC code, whether it's the punch or the route process. We'll kind of take a look at both of those. So this is exactly what the NC code is doing. So now we're not necessarily looking at the nest, but you can see all the different tools that are being used inside of that backplot. So we're going to see all the different sheet cuts, the tabs, all that stuff, and the positions of those tools. And now we can check out things like punching sequence, order, things like that, tool priority, and make sure all those settings are correct for what we want to send down to the machine. So we take a look at one of the ones for the router as well. And you can see here you have all your different drill cycles. And again, you can check out things like sequence, what's going to be cut first, which internals, which shapes, all that kind of stuff. You can see the different lead-ins and lead-out positions on some of the shapes. So you can see some of the tabbing that's done there, the different lead positions. Here's some of your sheet cuts that are being processed. So we can check out all that information as well. If everything looks good, we can select those plates and we can push those on to the next process. So what this does is it compiles all of those particular pieces of NC code, and it sends them to either a particular folder or drive to where the operator can then reach those. It also changed the status to sent. It updates any of your remnants, sends them back to inventory, all in that one action. Once you have feedback from the shop that material's been cut, those NC files have been run, you can update this status to cut. And internally, what that's going to do to TruNest is it's going to put that particular nest or order on a timer. And we can automatically purge those plates and parts from your orders to kind of keep the database or the amount of orders that you have in the system kind of more clean, more agile. So we're not storing things from, 5 or 6 years ago. However long you want to store things, you can set that setting. But if you want to use this status, it is there so that it will automatically purge these things and kind of keep your environment lean and running fast. So additionally, you can create things like a DXF or a PDF of the nest. You can do a print or plot of the nest as well if you wanted those for your shop travelers, things like that. So there's a couple other things that I wanted to show. So we'll go ahead and bring those up. And then after I show those, I think we'll open it up for questions. So we did a test. There's a couple different options, especially for the punching, that are pretty interesting. So we're doing a test between regular nesting versus what we call limited common line nesting versus full common line nesting. So a common line situation is where we're sharing part edges, things like that, in order to be able to be more efficient on the machine and not have to cut as much around each shape. So in the example that you see here, I took some of the parts that we just nested that kind of are the same length and really give us a nice common line scenario. I nested them in a regular orientation, so you could see a normal separation between each part, normal tabbing, normal sheet cutting, all the different stuff there. So in this case, we are processing and punching the material in its maximum. This is the maximum amount of punches that we're going to see from these particular parts. If we do something like a limited common line, what it's going to do is it's going to kind of match some parts up that have similar geometric properties. So in these cases, you can see nesting actually flipped some of these parts and put them back to back. And then we're actually doing a shared cut between those parts. And what this does is it's not a full common line solution. Full common line solutions can be tricky depending on the part mix that you have. So if you have a lot of rectangular parts, full common line is actually very useful. But if you have a mix of parts that, some are more contoured or don't necessarily line up with some of the other parts, a limited common line solution will cherry pick the parts that it feels go well together and will start to leverage common line between those two parts. And what that does is it kind of limits the amount of voids or areas between the parts where you have to destruct them now. And it ultimately makes for a safer solution that doesn't necessarily need to be monitored as much as a full common line solution. So in this case, this would be an area, because we merge these two parts together, that we need to fully destruct and make sure it's fully destructed so we don't get any floating pieces or material in those parts. So in this case, just from that, we actually save about 6% on the amount of hits for these parts, just from a limited common lines scenario. So in this case, it's probably about 30, 40 hits on the machine just by doing this process. And then a full common line situation, you can see now all the parts are full common line in between them. Again, we run into these situations where we need to make sure that we destruct the material between the parts in order to make sure that the sheet is processed accordingly. But in this case, we're going to save the most amount of punches since every line between these parts is shared. You can see the difference in material utilization as well. We're using less of the material up top here, so we could potentially fit you know, 1 or 2 more parts as well on the sheet. And we're saving close to 10% now from the original nest, about 65, 70 hits in this particular case. So all those savings add up over time, over nests, and really contribute to an ROI, things like that, for automated solutions like TruNest. So I wanted to show that off. So Rob, I'm sure there are questions. So why don't we kind of take a look at those and see if people have some questions we can answer.
I'd like to say that there are questions, but I think you did a great job because nobody has any questions.
Good.
So,
Awesome.
but yeah, if there's anybody that has any questions, either raise your hand or just go ahead and type it into the questions box. If you guys do have questions that you don't wish to ask at this point, go ahead and send us an email and we'll try to send it back to you answered, or give you a call, one or the other. But yeah, Matt, we don't have any questions at this point.
Okay. So I'll leave it open just in case somebody's typing out. There were a couple different things that I wanted to show as well. So I did this on purpose. And if we don't get any questions still, we'll kind of kick it off to the team. So there's a couple different things that I wanted to show as well. So one of the things we didn't really see on some of the parts or dive into was some of the cluster punching capabilities that TruNest has. So you can see here on a part like this, you know, I called this out when we were investigating the part assembly as something that I don't necessarily want to drill holes into this part with a router. It would just take way too long. And with a punch, especially a cluster punch, it's going to be a lot easier and a lot faster to produce this part. So what a cluster punch is multiple tools in a row or in a grid that I can potentially save hits as it's patterned out on a part. So you can see here the blue dots are actually the center hits for this particular cluster, and each cluster is actually skipping one of these. So it is a 1x3 cluster. So it's 2-inch spacing. So it's actually doing this punch here in the center, and then it moves over 1. So it actually, in 2 hits, it gets all 6 of these particular punches at the same time. And then it goes through and it does the same thing over here. So now we've eliminated for every particular run, we've eliminated, let's see, 4 punches for each time, 2 punches for each time the cluster runs. So we're essentially cutting this in, you know, by 60% by using that cluster punch tool for time savings. For parts that are kind of off-centered and not necessarily optimized for this tool, we can go back and single hit the ones that don't necessarily fit with that cluster as well. So just some different results. And on this nest, we have both these parts actually and a different kind of cluster. So this one is a 2x2. So it's in a grid of 4. So you can kind of see the different center hits there that we're saving for this part as well.
Okay, we do have a question from Barry. With regards to sheet cutting, can you dedicate what size the cuts for sheet cutting create to keep within a weight restriction for lifting? He's got an example here. It's 7H. Our Pro may be 18 inches wide, and the 11HR Pro may be 32 inches wide.
Well, that's a great question. So let's take a look at one of the nests that we have here and take a look at some of the sheet cuts. So you'll see that these sheet cut lines here are fairly evenly spaced apart. Go ahead and just kind of measure from one to the next one. So about 47 inches between those two. So it's really dividing this plate up into 3 pieces. So if you have stock sheet sizes like 120 by 60, 48 by 96, you can tell this particular optimizer to divide it every so often in X and every so often in Y, so that you can adhere to a particular weight. So if you know that 30 by 40 is a particular weight, and that is the maximum weight that you want to restrict, then you can set up your sheet cut to be those particular dimensions, and it's always going to be less than that. Because as we're removing parts, we're removing pieces of that skeleton. So you can closely monitor by weight how much of the skeleton that you're removing. So that's a great question.
And he says, thank you.
You are welcome.
Yeah, no more questions right now.
Okay. Well, I think that's all I had. I do have, I'll bring this slide up again just so you guys can see it. If you do have any more questions for either myself or Rob at SolidCAD, here's our emails and our websites where you can go ahead and contact us, ask us for some more information. We'll be happy to answer any additional questions that you have.
Yeah, I posted the the third of our series, part 3, which will be in July 7th. I posted that registration in the chat window. So if anybody has still not registered, click that one, go ahead and register, and tell a friend. It always works. So thank you, Matt. Thank you for your time today, guys.